What's up, guys? Welcome back. Episode, man, 67 maybe? I don't even know. I think 67. I am not feeling the best today. For some reason, I have a little bit of a headache. My nose is kind of clogged. A little bit of a sore throat, so I'm getting a little sick. So it might not be the longest video out there because I might go grab some things from Walmart. I really want to get a lamp for this room. Um, how much are blue light glasses, dude? Thing is, I wear glasses. How the hell would I wear blue light glasses? Okay, anyway. Let's take a look at Pokemon 67. I think we got a Machoke here today. A Machamp, though. Machoke. Damn, did I play that one yesterday, bro? No. Machoke Cry. Oh. Look at this guy, bro. This guy's huge, bro. Huge, like, lizard, bro. Ba-doop. 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 I don't even know how to do it, dude. It sounded probably so stupid, but yeah, bro. That's our Pokemon start of the day. Let's take a look at a few problems on Leetcode. Maximum candies allocated to K children. Seems like a binary search problem. Given a zero index array of candies, each element in the array denotes a pile of candies of size candies high. You can divide each pile into any number of subpiles, but you cannot merge two piles together. I knew it was binary search, baby. I'll be back. My friend's calling me in 1 second. I'm back. My buddy just called me. To be honest, I'm really bad at the binary search problems, I'm gonna lie. I find it hard to kind of think about. I actually got a notification on my phone this morning when I woke up that Leetcode made a video about this, so I think I'm gonna watch that video. Maximum candies. Okay, let's just look at that. 14 hours ago.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, maximum candies allocated to K children. This is the type of problem where if you were able to solve it, you probably like it. If you weren't able to solve it, you're probably going to hate it even after you see what the solution is, because it's one of those where it's like, it seems like it could be solved like several different ways, and maybe there are multiple like solutions to this one, but in a way it kind of leads you down the wrong track. Now, of course, I'm going to explain like how to approach this problem, try to explain the intuition, go through a dry run, go through the complexity analysis, and then we'll code it up. But people always ask, what's your thought process, Leetcode? Like, what was your actual thought process? But what if you can't handle my thought process? Well, I'll show it to you right now. I've been making comments to like explicitly have my thought process written down, and sometimes this kind of helps me approach the problem. For easier problems, it's kind of a hurdle, but I do it anyways. So first, let me just read the problem to you, and then I'll show you my thought process, and then we'll just get into the solution. The idea is we're given an array, I believe, of positive integers, and so we could have one that looks like this, 5, 8, 6. And then we're also given a parameter k, in this case, it's 3. The idea is we want to take this array, and we're allowed to take any of these numbers and split it. We could split it any way. Like when you say split, it doesn't mean divide it by 2, like divide this into 4 and 4. We could split it anyway. We could have 8 different 1s, or maybe we could have 4 different 2s, or maybe we could have like a combination. We could have a 3 and a 5. Already for me, this is seeming kind of complicated. Now what we want to do is have at least k integer different one, divide it by, and we're allowed to take any of these numbers and split it. We could split it any way. Like when you say split, it doesn't mean divide it by 2, like divide this into 4 and 4. we could split it anyway. We could have 8 different ones, or maybe we could have 4 different 2s, or maybe we could have like a combination. We could have a 3 and a 5. Already for me, this is seeming kind of complicated. Now what we want to do is have at least k integers. So we want to divide things up such that we have at least k integers. Right now we already have k integers, and we can have more than k integers as well, but what we want to do is then among those we want to pick the k largest integers. So if we had a bunch of integers, we just want k, so in this case we just want 1, 2, 3 of those, and we want to pick the largest ones because we want to give a pile to each kid. And I guess when I said we want to pick the k largest, it's a little bit misleading, because we want all k kids to be able to have the same number of candy. So we want to have k different piles that are equal, and what we want to do is try to make those k piles maximal, because that's what we're trying to do. Give each kid an equal amount of candy and the maximum possible amount of candy. And we're only allowed to take these integers and split them up. We are not allowed to merge integers together. So you can't like take multiple piles and then combine them. So knowing that, one of the first things that I thought of was, well, if we already have k piles, why would we ever want to split it up into more piles? Maybe like that's a case where we don't actually need to do anything. Maybe that's when we can stop searching or stop splitting things up. But that's actually not the case. Let me give you an example. What if I had a 1, 100, and 100? Well, if I take one of these 100s and I split it up into 50 and 50, now I have this pile over here, which I can also split into 50 and 50, and then I'll end up with at least three piles that are equal, and they are each 50. I believe that's the result for this example if k was equal to 3. So it's not true that as soon as you have k piles, you can stop. Because if you could, well then it would be pretty easy. You could just take the minimum value among all these 5, because we know that any other pile can be split up such that it can be turned into a 5 and then some other remaining integer. But that's not possible in this case. The other example shows something that's kind of interesting. This edge case is kind of a shortcut. What if we had like a 2 and a 7 and k is equal to, I think 12 or something? Well, in this example, the total sum of the candies is only 9. We can't split it up into k different positive piles. So therefore, like even though we can have 9 different piles of 1, we don't have 12 piles. So the minimum value from that is kind of 0. So the maximum that every child can get is going to be 0. Okay, now let me kind of just show you really quickly what my real thought process was when approaching this problem. So like these are the notes that I took. Sometimes I take these to help me solve a problem. Sometimes I take these for easy problems just so that I can have some steps that I can explain in the drawing explanation of these videos. But you can see I kind of covered.
I'm going to take a look at this problem the next day. To be honest, I'm just not feeling good right now. So I think doing a problem that requires a lot of thinking like this probably, you know, I'm like zoning out in the video. I'm just like not feeling good. So I think what I'm going to do is, we're going to jump into like a different solution. I want to do some binary search problems, but let's do like one tree problem or something. Sulo's common ancestor. I don't know. Okay, given the root of binary tree, return the lowest common ancestor as deepest leaves. Recall that the node of binary tree is a leaf only if it has no children. Oh, okay. Is there a way that we can check that this is the lowest part of the tree? I'm trying to think. Did we look at this one? Maybe we did. Yeah, we did. We're doing BFS here. What are we doing? We're checking. Well, it's a leaf node. Um, is BFS the correct approach here? Do a post-order traversal. Then if both subtrees contain a deeper sleeve, you can mark this node as the answer so far. Post-order traversal. Okay. Oh, jeez. Um, Post-order traversal is one that's like I'm not the best with because I think that's one that's tough to implement. Like, getting another call. Okay. DFS, we want to pass in our node. We post Is it post-order traversal? Right. Post-order traversal. Follows left, right, root. Left, right, root. Okay. What do we want to do? We want to create two variables. Okay, so left depth. Okay, so the thing is with this solution is we do a post-order traversal, right? Keep going through, so we go left. We keep track of its ancestor, its parent, right? And then when we find the deepest node, we just return its parent. Alright, that parent right. Dot right. Okay, so in this case here, we're gonna go all the way left. Then we're gonna return. We're gonna go left, turn right, come back, right, left. I don't know how to keep track of the left depth, DFS node dot left, parent left, parent right. If not node, return left depth, parent left, right depth, parent right. How do I keep track? Keep track of parent. If left depth is greater than right depth. I just don't understand how I keep track of the depth and then return the parent. Like, oh my god, dude. I think that's better. We do like the depth here. We take the depth. Left depth, parent left, node dot left. And we do depth plus 1. Depth plus 1. Right. The LCA, the deepest leaves is already found. Dude, this is confusing as hell. See, what I don't understand here in this code here is that we're keeping track of the actual node, not the depth. If left depth is greater than right depth, return left depth, left LCA. I'm just gonna write it in here. I'm not sure though. If left depth, I can't even say it, is greater than right depth. Sorry, ours is different. Ours is like this. Right depth. Return left depth. Left parent. Else if we have to look at the opposite, right depth is greater than left depth. Return right depth. Right parent. And then the last case is if they're equal. Both sides are equal. Node is lowest common ancestor. Return left depth node. That's what I don't understand. Why are we comparing the nodes? Like the nodes himself. I don't. Return DFS roots, and then we want to okay, bro. Depth. depth, right depth, return left depth, left parent. Right parent is not defined. Parent right. Parent left. Okay. I just don't understand this code, bro. Like, I don't get this part. Like, I get this, you know, if it's an empty node. If the node is null, we want to return the depth, right? Obviously, that's our base case, right? And then we're iterating here. We're recalling our function here. But then this part here where we're checking if left depth is greater than right depth, I just don't understand. I don't understand, like, how we're comparing the actual node and not the depth anywhere. Like, it's like, if the left depth is greater than the right depth. Why are we comparing the actual node? Yeah, bro. I'm just confused. I think I'm confused as well how this recursion is working. Like, I'm gonna leave this problem. Let's try another one. Let's count complete tree nodes. We already did this, bro? What the? Given the root of a complete binary tree, return the number of nodes in the tree. Oh, yeah, we did this a couple days ago. How did we do this, dude? Oh, that's right. We designed algorithm less than man. Man, today we're taking elves, dude. Can the root of a binary tree return its maximum depth? Given the root of a binary tree, return its maximum depth. Okay, a binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest node. 39, 20, null, null, 15, 7. Output is 3. That was loud, bro. From the root node down to the farthest lead node. Oh, okay. Maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So 1, 2, 3. Okay. I was thinking about the other problem where you had to find the longest path from any node. I couldn't remember how I did that one. How we did that one. I remember watching the video. Okay, we're gonna do a recursive approach, and then we're gonna do a iterative approach because I think we should be able to do both. I'm hoping. DFS root. Okay. The depth. You pass in 1 as our depth. We don't want to. No dot left DFS. No dot left is equal to DFS. No dot left. Left. Dude, can I talk today, bro? Like, oh my gosh. No dot left. Depth plus 1. Man. Okay. If not node, return. Okay. Let's just implement DFS. Today is just not my day, bro. I think I'm just not locked in. Okay, we return our left and our right. This is DFS right here, right? Right, so pretty much what we're doing is that we're looping, right? But now we need to if no dot left, we want to call this, right? And if no dot right, we want to do this, right? So this is our recursive case, right? This is our base case, right? We want to pass in our depth as well, right? Start our depth at 1, because that's what our root node will be, right? And then we always pass in, well, depth plus 1. Depth plus 1. We want to return our depth. I think I'd find the maximum depth. Yeah, using DFS, but it has a few issues. Okay. What if all maximum depth of binary tree? I'm not trying to. Return the max of left depth, right depth +1. Turn DFS route. We don't need this anymore. +1 includes the root node, I'm pretty sure. Bro. Counted. bro. Node 7 is elite now. Okay, I'm gonna think about this recursively, dude. I am not feeling good right now, so this is probably a terrible video. I mean, I haven't even solved the problem. I'm just being 45 minutes, so okay, we got our base case here, right? Actually, let's draw this tree. 3, 9, 20, 15, 7. Right, so we start off with a node. Do DFS node to the left, so we go here, right? And then we do a left here, okay? Again, this is a null node here. So then we return 0 here, right? So we're returning back into this function a 0. Then we get to the next point, right dot left, right? So then we go here. We return back a 0 as well. So this is a null node. Then we come here and we check we return the max of left depth and right depth, right? Left depth, right depth both return 0. So then we return the +1. So then this returns 1. Then it goes back to the 3 here. And we do a node dot right, which goes here. Okay. We do a right depth is equal to DFS node dot right. Okay. And then we do a left depth, which we go down here. And then we do another left depth, which goes here, right? Then we go to 0. We come back here, goes right here. We get another 0 here, comes back here. Does the max here. This is a 1 as well. Then comes back here. Then we do the right here. So we go node dot right for this one. Goes to here. Then does its children. This is a 0. This is a 0. Then returns 1 back to this one. Then we compare 1 and 1. So this returns 2. Then we come over here. And then we return finally the max of 2 and 1. 2 plus 1, which is 3. And we return 3. That is how that thing works. It's just hard for me to like think about it in that way, bro. Like, it's so tough. Like, alright, we're gonna do the iterative solution. Kind of taking L's today, bro. Like, straight L's. Do our while stack. We want to pop out node from our stack. Node is equal to stack.pop. Right. Well, if node dot left, then stack dot append node dot left, node dot right, stack dot append node dot right. And we just want to Somehow we need to keep track of our... I think we need to keep track of our depth, right? Is equal to stack.pop. No dot left. Then our depth plus 1. And our depth plus 1. Yes, we can take the res is equal to the max of our current res and our depth. And I guess we just want to return our res. I don't know if this will work, but maybe it does. Nice. Woo! We did the iterative solution in like 2 seconds. No, we didn't. Damn. There's no attribute left. There we go. What do they do here? They do def count non-local max depth. I'm actually not sure what non-local is. Cool in Python. Side of nested functions. Okay. Yeah. Let's take a look at some session problems or something. What are these again? I think these are all typical. So, didn't we do this one, dude? Did we not submit it? No, we didn't submit it, bro. Oh. Peak index and amount of array. Let's take a look at this one. You're given an integer mounted array of length n, where the values increase to the peak element and then decrease. Return the index of the peak element. Task to solve it in overlog n. So it is a binary search. Why do we output 1 here though? I don't know. Why do we output 1? Oh, we're returning the index of the peak element. Okay. Okay. Even an integer amount of array like then where the values increase to a peak element peak and then decrease. Return the index of the peak element. Low is equal to 0, high is equal to the length of array. This one. Low is less than or equal to high. We want to calculate our mid. Our mid, right? So our mid is equal to, well, high plus low over 2. That seems wrong. No, I mean, that's right. Okay. All right. Calculate our mid, right? Then we do, well, okay, well, if array mid unless an overlog n, we can't do max because max is O of n, I think. Yeah. Back into summer 2000s. High plus low. Try to think here. How would we implement this? We're trying to find the peak, right? Okay, if array mid is less than array mid plus 1, peak is to the right, then we set mid is equal to, sorry, low is equal to mid plus 1. Else if array mid is less than the array mid plus 1. Else if array mid Okay, this needs to be an else because it could be at the current section. That's why I think it's failing. It could be at the current index. Bro, I need shit so bad. Oh, damn. Okay, no. There we go. Okay. All right, sweet. I'll be back. I gotta go to the bathroom. 1 second. All right, guys, we're back. Gonna do one final problem. Probably gonna go to the Leetcode 75. Just pick a problem from there. Man, I am like. Let's do string comprehension. We took a look at this one yesterday or someday. I don't know. Oh yeah, that's right. You must write an algorithm that uses only constant extra space. Rawr. Yeah, no, not this one. Let's take a look at an increasing triplet subsequence. Return true if there exists a triplet in indices I, j, k, such that I is less than j. I wonder if the O-Van square, I mean, there's an n-cube solution. If I is less than j is less than k and nums I less than nums j is less than nums k, and we can return true. Otherwise we just return false. I don't think this will submit. Like, will it? Probably not. No. Yeah, no, it does not submit. So we need to optimize this. How can we optimize it though? How can we make this O of n squared? The idea is to track two values, the smallest number counted so far, the second, the smallest number greater than the first. As we go through, we find a number greater than both first and second. We have found an increasing triplet subsequent. Oh, that's a pretty good way to think about it. Well, we'd have to sort though, right? Like, second is equal to float infinity, right? Then we loop. We do while for Oh no. Well, sorting it won't work because we have to keep track of I as well. So sorting it won't work. Also, if nums I is less than or equal to second is equal to nums I. List index is out of range. Yeah, we don't have it. We're not doing a range. No way that worked. For I nums, if I is less than or equal. Wow. What a problem. I want to do another binary tree problem. When did I do this one? Yeah, recently. Let's reset this code. Binary tree root, a node x in the tree is named good if the path from the root to x there are no nodes with a value greater than x. Given a binary tree root, okay, given the root, a node x in the tree is named good if in the path from root to x there are no nodes with a value greater than x. Well, we need to somehow keep track of. That is equal to sec that pop. Well. The amount of good nodes. Good nodes plus equal to 1. If or 10 good nodes. Two null 4. We're processing the root node anyway. I don't know what it is. Leetcode 1148. Logically, where you're comparing node value, the root node is incorrect. You're comparing each node's value to the value of the root node, which doesn't take into account the path from the root to the current node. You need to track the maximum value and count it along the path to each node. Okay. Okay, do I have to... This is max node now. I'm updating it. Oh, okay, so I'm updating it globally. They're saying it needs to be within here. Max node. Root.val. Pop here, max node. Cannot unpack non-iterable int object. What? Dude, what? What is going on? Cannot unpack non-iterable tree node object. Oh. Do we need this? Is that what's causing it? No. Root.val cannot unpack non-iterable tree node object. Bro. There we go. Okay. Okay, now if I were to do DFS, how would I do it? That's the tough part. I'm gonna need a root. I'm gonna need a root.val. Okay. How do we do this? Okay. And the left is equal to it's associated outside of the function. That means I gotta pass in good node. Yeah. That's nice. Curious what my first solution was, bro. Count. Okay, we passing our count. Okay. Interesting. All right. I'm gonna call it there. Appreciate you guys watching. Sorry, probably the video didn't start out as well in the beginning. I'm just, I don't know, not feeling good. But yeah, gonna probably do some other stuff around my house, and I will see you guys tomorrow. So, thank you. See you later.